Now, graphs representation. If you want to write an algorithm on a graph, the first question that you should ask yourself is how to represent the graphs. What is the data structure to represent the graphs? In fact, it is not only represented by matrices. So the title is not correct. So we should not say matrix representation. We should say representation of a graphs. The first representation is by using adjacency list, which is like a linked list. When we say adjacency list, it means we describe each vertex by its adjacent vertices, and we put that one in a list. For example, the vertex A, it is adjacent to C, D, and E. So we put C and D and E in a list. So A is pointing to this list. Now, what are the adjacent vertices to B? We have only one, and we put that one also in a list. What are the adjacent vertices to C? We have B, A, and D, and we put those vertices in a list, and we let C points to this list. And now for D, there is a loop. And since a loop is a vertex that is adjacent to itself, so we will put the adjacent vertices for D will be C, A, E, as well as D, and put them in a list, and let D points to this list. Let me show you a picture of this linked list more closely. Here is a picture of the linked list more closely. So this is like an array of pointers, and for each entry in the array represents a vertex of the graph. Now for A, the first entry in the array for A will be a pointer to a list for all adjacent vertices of A. And for B is the same, and for C, so C is pointing to A, the adjacent vertices for C is A, B, and D. And now see for D, also since D is in the same list, then D is a loop. So what is the drawback of this representation? The definition says here that this representation is used for graphs with no multiple edges. In other words, it says that this representation is not suitable for multiple graphs. Graphs with parallel edges. Another disadvantage is the nature of the linked list. And you know that for linked list, we always traverse through the list sequentially. So there is no random access to the elements. The other representations by using matrices. The first representation is by using incident matrix. The other one is by using adjacent matrix. So let us first see how we can represent the graphs by using incident matrix. You can represent graphs by using two-dimensional array. So you have the first dimension will be the set of vertices, and the second dimension will be the set of edges. So we have rows, the vertices, and we have column, which are the edges. So the number of rows is determined by the number of vertices, and the number of columns are represented by the number of edges. In this case, we have to label the edges. We have to give them labels, A1, E2, and etc. The entries inside the matrix are either ones or zeros. And this is what does it say in the definition, that the entries inside are either 1 or 0. So what are these 1 and 0s? You go to the first vertex. If V1 is incident to E1, you put 1. So where is V1? This is V1. And CV1 is incident on two edges, E1 and E3. So this is why on E1, E2. So this is E3. So V1 has two incident edges, E1 and E2. So this is why we have 1 on E1 and we have 1 on E2, and all others we have zeros. And if you go, for example, for V4. For V4, the incident edges are E3 and E1. So this is why we have E1 and E3 we have 1, and all others are zeros. Now what about loops? You know that a loop is an edge. So you need one column for it, and see for E7. So E7 is one column for it, and if you look at all the entries in that column, we have only 1, because this one is only incident to V2. So what is the disadvantage of this representation? One, imagine you want to add an edge, okay, in here. Then what you need to do, you need to add a column. And you know that when you write a program and you create your array, then it is not possible to add a column or a row unless you delete the array and create a new one. So it is very expensive to add an edge. However, it is a very simple operation on graphs. Second, if you want to check for a loop, whether E7, E6, E5, and etc. is a loop, then you need to go over all the vertices, and if you have only one, then it's a loop. For example, E6, you have to check V1, V2, V3, V4, and V5. If it is incident only on exactly 2, then it is not a loop. But if it is incident on exactly 1, and how to check it is incident on exactly 1, then you have to go over all of these elements, which you also needs a loop that goes over all vertices, and this is also a simple operation that's supposed not to take this amount of time. Last, which is most important, is that it is not suitable for directed graphs. If you want to represent directed graphs, then you have to represent arrows. So how to represent an arrow that you have from V5 to V3? So this is V5 and this is V3. So is there an edge between them? If there is an edge between them, which is E5, now there is an edge between them, C, we have consonant. But how to tell that this is going from V5 to V3 or from V3 to V5? Now the last representation for matrices is called adjacency matrix. Now for adjacent matrices, it does not compare vertices with edges. It compares vertices with themselves. So the matrix will be a square two-dimensional array represented by the number of vertices. And it can represent directed graphs, and it can also be represented for undirected graphs. Now for directed graphs, how to build the matrix. It is a two-dimensional array, and the two dimensions will be the same, represented by the number of vertices. So what will be the entries inside the matrix? It will be the number of arrows going from Vi to Vj. So the entry for Ai inside the matrix will be the number of arrows going from Vi to Vj. Now for undirected graph, we don't have arrows. Again, it will be a square matrix. Rows and columns will be the number of vertices, but the entries will be the number of edges connecting Vi and Vj. So the entry for Aij will be the number of edges between Vi and Vj. Let's go for an example. Here there are two examples. One is for directed and the other one for undirected. Now for the directed graph, here we have 3 vertices. So the size of the matrix will be 3 by 3. Now the edges representations will be by the entries inside. So we will compare each vertex by the other vertices. Now for V1, how many arrows do we have from V1 to V1? Nothing. How many arrows do we have from V1 to V2? Nothing. And how many arrows from V1 to V3? Also nothing. So no edges from V1 to all other vertices. Now for V2, there is no edge from V2 to V1. So it is 0. But there is an edge from V2 to itself. There is an arrow, sorry, I have to say an arrow. And also there is an arrow from V2 to V3, 1 arrow, so we have 1. But if we go to V3, there are 2 arrows going from V3 to V1, so this is why the entry between V3 and V1 we have 2. And there is 1 arrow going from V3 to V2, and there is no arrow that's going from V3 to itself. For undirected graphs, the size will be determined by the number of vertices. So we have 4 vertices, so the size of the matrix will be 4 by 4. And then we will compare each vertex with other vertices. So there is no edge between V1 and V1, so it is 0. There is 1 edge between V1 and V2. There is no edge between V1 and V3, and there is 1 edge between V1 and V4. Let's go for V3 now. Now for V3, there are 2 edges between V3 and V2, but there is no edge between V3 and V1, and there is no edge between V3 and V4. Now for V2, we have an edge from V2 to V1, and there is an edge from V2 to itself, and there is an edge from V2 to V3, and there are 2 edges from V3 to V2. So inside the matrix, it represents number of edges. So if I want to add an edge, it is simply like in C++, you just say the name of the array, which is the two-dimensional array, plus a plus. So there is no need to delete the array and then build a new one like the incident matrices. And also it can be used for directed and undirected graph. Now how to check if there is a loop and how much time it takes to check for the loop for adjacency matrices. Now if you want to check whether you have a loop, let's say around V2, then there is no need to check all the other vertices. Only check the diagonal. See if this is the diagonal. For V2, check the on the diagonal between V2 and V. If there is an entry, then there is a loop. And if it is 1, then there is one loop. If it is 2, there are 2 loops, and etc. So it is just a testing. If you want to check that there is a loop around V4, then in C++, you say if A, the name of the matrix, 4 and 4 greater than or equal to 1, then it is a loop. So it is a simple test. It's not like incident matrices, then you have to go over all vertices to count how many incident edges. So this is more efficient than incident matrices and more efficient than adjacency lists. Now if you are given the matrix representation of a graph, how to tell from the matrix representation that the graph is simple or not? Remember, when a graph is simple, if it has no loops and no parallel edges. So first, how to know that there are no loops? If you want to know that there are no loops, you need to check the main diagonal. So check the main diagonal, and if there are no ones on the main diagonal, then it has no loops. This is one. Next, how to check if there are parallel edges or not. And you know that the entries inside the matrix represents number of edges between vertices. So if all entries inside is 0 or 1 only, then it does not have any parallel edges. But notice here we have 2 and here we have 2. It means between V3 and V2 there are 2 edges and they are parallel, so the graph is not simple. One more thing, if you have undirected graph, then you will notice that the matrix generated will be symmetric with respect to the main diagonal. So here we will write symmetric with respect to the main diagonal, which is in blue color. Now notice now here, we have like see, this rectangle is the same as this rectangle. So here we have 1. If this is like a line and this is like mirror, so here you have 0, here you have 0, here you have 0, here, so 1 and 1. Why? Because if there is an edge between V1 and V4, so definitely there is an edge between V4 and V1. So it should be symmetric. So here is the conclusion. If you have directed graph, then the matrix generated is not symmetric. If you have undirected graph, then the matrix generated will be symmetric. Now let's go from right to left. If the matrix is not symmetric, then the graph is directed. Now if the matrix is symmetric, it is not necessarily that the graph is undirected. Let me show you an example. This is an example with a symmetric matrix. And now I can ask the following question. Is M, okay, so if this is the matrix MG, is MG matrix for directed or undirected graphs? Okay, so the answer, it could be both. Now if it is undirected, then it is very easy to draw it. Now if it is directed, Then how to draw it? So we will have 4 vertices. I will put them just randomly on any place. Now we have an arrow from A to A. So this will be a loop. And we have an arrow from A to C. So we have A to C. And we have an arrow from A to D. So we have an arrow from A to D. Here I'm talking about the first row. Now for the second row, we have an arrow from B to D. So we have an arrow from B to D. Now for the third row, we have an arrow from C to A. So we will have C to A. And also we have from C to C, which is a loop. And now we go for the last row, we have from D to A. So we have from D to A. And we have from D to B. And this is a directed graph. What can you notice from this graph? If this is a matrix for undirected graph, then if you want to convert it to directed, for each edge, there is an edge that is going and there is an edge that is coming. So if you want to convert this graph into undirected, simply remove these two and put one edge. Simply remove these two and put one edge, and simply remove this one and put one edge. Consider the following example. It says the following is an adjacency matrix for a graph. So the graph has 5 vertices and the entries inside are only 0 and 1. And we have some questions. Before we start answering these questions, is this a graph for simple graph or not? So if you want to check whether it's simple or not, check that it does not have loops and does not have parallel edges. So notice now this is the main diagonal. Since all the entries on the main diagonal are 0, so we don't have any loops. And also entries inside, since all the entries inside are 0 and 1, so we don't have parallel edges, so it is a simple graph. Now, is this for directed or undirected? If it is symmetric, then it could be both. If it is not symmetric, then it is definitely for directed graph. So you check for the main diagonal, and this is the main diagonal you have, and see if it is symmetric or not. So here you have to look for this portion. It should be reflected in this portion, and by testing each entries on top, you will find them in below the main diagonal, so it is symmetric. So it can be directed and it can be undirected. First question, how to find the total degree from the table? Now this question is like asking you to write a program. You have a matrix, 2-dimensional array, and how to find or how to write the steps to find the total degree. To find the total degree, what you have to do, you have to add all the entries in the table row by row. And any of the entries is on the main diagonal, you just double it. And how to check if it's on the main diagonal? If the row value and column value are equal. So you write nested loop, and inside nested loop, you just simply have a variable for summation and you add all the entries. But before you add the entries, the values 1 and 0 to the summation, check if it is on the main diagonal or not. So if row equal column, you multiply by 2. Next, how to find the degree from the table for vertex C. You find, like what we have done for the degree, you find the total of all the entries on row C, and if on, let's say, the entry C and C, there is 1, you just simply multiply it by 2. Not only 1, probably there are more than 1 loop. If it is not simple, you simply multiply it by 2. How to show from the table if there is a loop incident on D. Where is D? So you have to check the intersection, which is this one. So you check this entry. If it is equal to 0, then there is no loop. How to show from the table that A, B, E, D, C is a path. So we have to follow the path from the table. From A to B, first let us check from A to B. Is there an edge from A to B? Yes, there is an edge. Let's go to the next one. B to E. Do we have an edge from B to E? Yes, we have an edge. Next, between E and D, do we have an edge from E to D? Now, as you notice, we have no edge between E and D, so this is not a path in the graph, and this path does not exist.